I'm going to solve another problem with constant acceleration due to gravity. This problem is a little bit counterintuitive, but it's going to confirm something that we learned in a previous video. So we're told here that a ball is thrown horizontally at 2.2 meters per second. A second ball is dropped from rest, and they both start at the same distance above the floor. How long does it take each ball to hit the floor? So if I mark these two graphs, I have two graphs because it's two separate objects. So if I say this is 1.5 meters, then what is the trajectory of these two objects? What is it going to look like for these two objects? So starting with the ball that's dropped from rest. So this is kind of the simplest trajectory. I'm just going to write it here, and the trajectory of this ball is going to be downward. On this 2D graph, the ball is going to fall straight down. And what will the trajectory be of the ball that's thrown horizontally? And so I'm going to draw this also just offset to the right just a little bit, just so we can see it a little better. You could also draw this on top of the y-axis. I didn't do that because I have a straight line path here, so I just want us to be able to see this clearly. But if you have, starting from the same point now, and this ball is thrown horizontally, so its path is going to be basically half of a parabola. So it's going to fall in that direction. So we have these two different cases here, and we're not given a whole lot of information, but what can we do to solve these? Well, what we're going to be doing now, and you're going to have to think back to how motion was treated in the previous problem with constant acceleration due to gravity, how motion was treated in the horizontal and the vertical directions. So let's write some things that we know. We're going to have two separate cases, two separate kinematic equations, because we have two separate objects. So if I look at just this first object, I'm going to call this delta y1. And I'll write this is object 1, and this is object 2. So delta y1, well, what does this mean? This means y final 1 minus y initial 1. And where do we end up? What is the final position of this object? Well, it reaches this y equals 0 position. 0 meaning 0 meters, that's the ground. So this would be, the final would be 0 minus the initial, which was 1.5 meters. So delta y1 is negative 1.5 meters. All right, so let's look at the second object. What is delta y2? Delta y2 is equal to y final 2 minus y initial 2, which is the same. We end up at the floor, so 0 meters. And we started at 1.5 meters. So delta y2 is also negative 1.5 meters. And what acceleration do we have? What's another value that we know? Well, the acceleration g is negative 9.81 meters per second squared, and this is pointing downward. So we have motion in the vertical direction, so clearly g is going to be working on both of these objects. Okay, so we have an expression for, and a value for delta y1, we have a value for delta y2. So let's write one of the equations of motion. So I'm going to start now with object 1, and the equation of motion for object 1 would be delta y1 is equal to, well, it's going to be the initial velocity in the y direction times time plus 1/2 gt squared. And let's see if we can solve this, if we have enough information to solve for one unknown. Do we know the initial velocity in the y direction? I haven't written it over here. We haven't discussed that. Well, what would that be? So for object 1, it's being dropped. So what's its initial velocity in the y direction? If you're just holding that ball in your hand, well, VIY is equal to 0 meters per second. And what would it be for this ball that's thrown? It says it's thrown horizontally at 2.2 meters per second. That means that it's thrown in the x direction with some positive x velocity. And I'm switching now to this second case, but I want to compare these. So look at this. So this one's being thrown with some velocity that's pointing this way. Does it have any initial velocity in the y direction? Well, this is in the x direction, so clearly it has some VIX. But what about the vertical velocity? Well, there is no initial velocity in the y direction. It is also 0. So VIY equals 0 for both objects. They're both just being, when you consider the vertical direction, they're both just being dropped. You have to remember that the vertical motion is independent of the horizontal motion. So although this is thrown horizontally, there is no initial velocity in the vertical direction for object 2. So VIY is 0 meters per second. That means this first term is 0. VIY is equal to 0. So then, well then delta y1 reduces to 1/2 gt squared. Do we know what delta y1 is? Well, yes, we figured that out over here. Do we know what g is? Yes, that's constant. So we can solve for t. So I'll go ahead and do that. I'm going to solve for t first by multiplying both sides of this equation by 2. So this becomes 2 delta y1 equals gt squared. I divide both sides by g, and this becomes 2 delta y1 divided by g equals t squared. And now I can take the square root of both sides of the equation and solve for t. So then t is equal to the square root of 2 delta y1 over g. Great, now I can put in my numeric values. I know what these are. So t, the numeric values then are 2 delta y1 is negative 1.5 meters. G is negative 9.81 meters per second squared. So I have a meters in the numerator, a meters in the denominator. Those divide to 1. And I have 1 over second squared remaining. Well, 1 over second squared, the second squared goes to the numerator. So I'm going to rewrite this now. I have 2 minus divided by minus is a positive number, so I get rid of the negative signs. 2 times 1.5 seconds squared over 9.81. And now I can start doing the multiplication and the division. So first I'll do 2 times 1.5 which is 3, and then I'm going to go ahead just to save some space here. So 2 times 1.5 is 3, and then I'm going to divide it by 9.81. So 3 divided by 9.81, and then this becomes the square root of 0.31 rounded to 2 decimal places, and it's still seconds squared. So now I take the square root of both these, the 0.31 and the square root of the seconds squared. So the square root of the numeric value, t, is equal to 0.55, and the square root of seconds squared is just seconds. So I have now solved this value and found this value t. So the time that it takes this ball, object 1, to fall is t equals 0.55 seconds. So now I'm going to do the same thing for the second object, and I have to remember that delta x and delta y are independent of each other for this object. So there is, a delta x2. We currently don't know what that is, but we have found what the numeric value is for delta y2. It still has to travel the same distance of 1.5 meters that the first object did. It's not like, since it's traveling in the horizontal direction, that somehow adds to the distance that it has to fall. So we're not sure about a delta x2, but we can now solve for this delta y2. So let's do that. So we have delta y2 is equal to VIY times time. Now, we've already said that the VIY for both of these is the same. We're using VIY because vertically they both start with 0 velocity in the vertical direction. This has horizontal velocity, object 2, since it's being thrown horizontally, but this person isn't throwing the ball downwards with some force. They're just throwing it horizontally. So when we look at the vertical direction, the VIY is again 0. And we know the other component of this equation is 1/2 gt squared. So we can treat this, we can neglect the first term because, again, VIY equals 0. It's starting from rest in the vertical direction. So what do we do then? Okay, so do we know g? Yes, we know g, and we know delta y2. We figured that out, so we can solve this. And you're probably already figuring out that it's the same as the t for delta y1. But let's just go ahead and solve this. So we can solve this again for t. So this becomes 2 delta y2 divided by g equals t squared. All I did is I multiplied both sides by 2, and I divided both sides by g. And then I take the square root, just like we did previously. T is equal to the square root of 2 delta y2 over g. And these values then are 2 times negative 1.5 meters divided by 9.81 with a negative sign meters per second squared. So the same exact value is right up here, and we see that t is equal to 0.55 seconds. And at this point, it can kind of be like, well, wait a minute, what about the horizontal motion? Well, recall from the previous video that this VIX, this horizontal velocity, stays the same throughout every point in this ball's trajectory because gravity is only working in the up and down direction. Gravity is pointing up and down, and it doesn't affect the horizontal motion. So if that's the case, the only thing that determines how long the object stays in the air is its height and the acceleration due to gravity. Well, its height is the same. They started both at 1.5 meters, and gravity didn't change for either of these. Gravity is the same pointing up and down on either one of these problems. So we can neglect the horizontal velocity. And that's really strange, even in the most extreme case. For example, if we drop another ball, say a basketball from 1.5 meters, and you have a rifle that is pointing perfectly horizontally, the amount of time that the basketball and the bullet stays in the air will be exactly the same. And that is so counterintuitive. We want to think that, well, the bullet is moving so fast, so it's going to spend so much more time in the air. But you can actually prove it. You can prove it experimentally. You can also prove it here just with the math. We've already shown that under constant acceleration, if it's only being acted upon by gravity, then that's the only thing that determines how its vertical velocity changes. So whether you were to fire a bullet perfectly horizontal from the same height as you would drop a basketball, they would both hit the ground at the same time.